I want to go ahead and welcome up our next session panelists for water quality, one by one to the stage, starting with Dr. Chris Anastasiou, then Dr. Miles Medina, Dr. Detong Sun, and Rebecca Cray. And I'll go ahead and introduce them as they're coming up. Dr. Chris Anastasiou is the Southwest Florida Water Management District's Chief Water Quality Scientist and Seagrass Mapping Program Lead. Dr. Anastasiou has been working in the Charlotte Harbor Watershed and Estuary for over 30 years, evaluating water quality, mapping seagrasses, and managing habitat restoration projects. Since 2017, Dr. Anastasiou has also served as the district's Emergency Operations Center Weather Operations Unit lead. This year, he has also taken on the lead role of the district's newly established EOC Water Quality Recovery Unit. He received his PhD in 2009 from the University of South Florida's College of Marine Science. Dr. Anastasiou is also a commander in the United States Navy Reserve with 18 years of experience as a naval meteorological and oceanography officer. Thank you for your service. Dr. Miles Medina of the University of Florida Center for Coastal Solutions is a quantitative eco-hydrologist focusing on coastal water quality and its drivers in Florida. Last year, he discovered a link between red tide blooms near Charlotte Harbor and nitrogen loads from Lake Okeechobee. He continues ongoing research on water quality trends in Charlotte Harbor based on approximately 20-year data set generated by the Coastal Charlotte Harbor Monitoring Network. Previously, as a quantitative consultant, he worked with various governmental entities and developed data management and machine learning tools to identify sources of water quality impairments throughout Florida. Miles completed his PhD in 2019 with a thesis on inferring causality in complex eco-hydrological systems, including treatment wetlands in the Everglades and red tide blooms off of Florida's Gulf Coast. Dr. Detong Sun from the South Florida Water Management District is a modeling expert for estuarine hydrodynamics, sediment transport, and water quality. With over 20 years' experience working on Florida's estuaries, he's played a major role in the development and application of hydrodynamic and water quality models for the St. Lucie River estuary and the Caloosahatchee River estuary. While numerical modeling has been his essential area, he's also interested in theoretical models and has developed a zero-dimension theoretical model, water quality model for the St. Lucie estuary and a one-dimensional theoretical water quality model for the Caloosahatchee River estuary. Rebecca Cray is an environmental specialist with the Florida Department of Environmental Protection's Estero Bay Aquatic Preserve Office. She leads Estero Bay Aquatic Preserve's continuous water qualities and seagrass monitoring programs and coordinates local volunteers as part of the larger Charlotte Harbor Estuaries Volunteer Water Quality Monitoring Network and has been with the preserve for over 7 years. Each of them is going to give a brief presentation on their respective topics. I will mention that you may have to pass the clicker around because you'll see the order of the presentations may not be the person next to you. So just go ahead and do that. We will open up Q&A now in Menti, so you can, as you hear the presentations, enter your questions, and at the end, as we did with the last panel, we will have the presenters answer as many as they can. So with that, I'm going to turn it over to our first presenter, which is Dr. Chris Anastasiou. Thank you.
Thank you, Jennifer. Good morning, everyone. So today I'm going to present to you some research that we've been doing. And this is a presentation that has been presented before. So those of you who have been in BASIS and then last year at the University of Florida's Water Quality Summit, this is some of the findings that we had. But I think it's important that for those of you who have already seen this, to really look at the information that I'm going to present to you here in the context of Hurricane Ian and what we're going through now. in this post-Ian environment. What I'm going to talk about today, though, is something that we've coined the term the hangover effect. And so it's an attempt to really look at some of the causality of the phenomenon that we saw starting around 2018 and then going on until 2020. So we're going to take you back in time a little bit. But again, think about this in the context of what we went through last fall. Just to orient you on where we are, obviously we all know we're in Charlotte Harbor, down on the very lower end of this slide. This is just a graphic showing you the 12 priority water bodies that the Southwest Florida Water Management District works in. And of course, Charlotte Harbor is one of the major estuaries that we do work in. Now, these are not numbered in order of importance. They just happen to be numbered in this way. So as we all know, Charlotte Harbor is a very large estuary. It's the second largest open water estuary in Florida. We have a relatively large, what we call a watershed to open water ratio, about 12-1, which means we've got a lot of fresh water coming into the system, primarily through the Peace River, but also from the Mayaca River, and of course a lot of the more localized tidal tributaries. So in part of what the district does is we create these things called SWIM plans. So SWIM is an acronym for Surface Water Improvement and Management Program. And in 2020, there was a SWIM plan that was updated. And part of that update was looking at the water quality, specifically nutrient loading from the Peace and Mayaca rivers. And what was concluded in this plan was that there was really no evidence of degrading water clarity, increasing chlorophyll A, or increasing total phosphorus or total nitrogen. And the reason why I wanted to mention this, because it's sort of setting up Miles and his talk coming up. There's some caveats to this conclusion. Number one, it goes up till 2017. A lot of the changes that I'm going to talk about here in the next few minutes really started in earnest in 2018 and on. So that's really important. The other thing that's important too is when we look at watershed nutrient loading from Peace and Mayaca River, we're looking at the gauged stations. So there's a limited number of gauge sites along the Peace Mayaca River. That doesn't really take into consideration the ungauged portions of the watershed, which we think could be very significant. So those are some things to keep in mind when we say that. So even though traditionally, at least up until, again, 2017-18, we thought about Charlotte Harbor as a relatively healthy estuary, there are a lot of caveats to that. So there's a big but there. And one of those big buts is also based on work that Gene Turner and others have done back, that was published back in 2006. And this was a paleolimnological study that was done by the district and LSU. And what we concluded from this work was that in 2000, so now we're talking 23 years ago, the nitrogen loads that were coming into the harbor, what the paleolimnological work suggested was still 3 times greater than what we would have expected back in the 1800s. So even though, relative to maybe some of the other estuaries that we see in the state and in the world, we would consider Charlotte Harbor relatively healthy. It is certainly not pristine, and we're seeing trends from 2017 on that would suggest that things are not getting better. In fact, they may be getting worse, and I think Miles is going to touch on that in a few. So one of the big things that we do at the Southwest Florida Water Management District is we map seagrass along the west coast, at least our portion of the west coast of Florida. The reason for that is because seagrass is an indicator of overall estuarine health. And so we've been doing this for a long time, and this is not a seagrass talk, so I'm not going to go into detail on how or the long-term trends in our seagrass mapping. But we do map seagrass as an indicator, and that's important because if you go back to 2018, again, going back to that initial slide showing that Charlotte Harbor was a relatively healthy estuary, a lot of that was also based on the fact that our seagrass trends really hadn't changed much over the last 20 years. You look from 1988 all the way up to 2018, things were looking pretty stable. Really wasn't a whole lot of change. So we were feeling pretty good about the estuary. And then 2020 hit. And this is where we saw a major loss of seagrass. And Kelly did a good job in this last session and kind of touching on that. In fact, you're going to see a slide that's very similar to one of the ones that he presented. And so we saw a lot of loss. And a lot of that loss was really centered around what we call the east wall of Charlotte Harbor. Here's the graph that you should recognize from earlier. That east wall really saw a huge loss of seagrass. About 50% of the grass was lost between 2018 and 2020. And so this was cause for concern. and started us thinking about what are some of the causative factors that might be behind this rather rapid loss in seagrass. Well, along with that, we saw a rapid increase or a gain in the percent cover of macroalgae, specifically drift algae. This species, Caulerpa fastigiata, which admittedly was relatively unknown to me, was very common along the east wall and the west wall as well, and a lot of the tidal creeks. But the FWC and the Aquatic Reserve was noticing just really huge amounts of this macroalgae, and it can be a drift algae, it's filamentous, but it can also be an attached algae. So it's a very relatively strange species of Caulerpa, not one that I have been used to working with. Caulerpa prolifera is one of the more common ones that I'm sure many of you are familiar with. But this particular type of Caulerpa was just ubiquitous along the east wall of Charlotte Harbor. And if you look at some of the data that FWC and the aquatic preserves put together, this again only goes till 2021, but you can see that there's a sharp increase in the occurrence of this type of macroalgae starting in 2018 and really continuing beyond that. And that's concurrent with their abundance data based on Brom Blanc measurements of seagrass. This is just one example at one of the stations along the east wall, but what it shows is that that loss in seagrass that we mapped between 2018 and 2020 is consistent with what we were seeing in the field using these data here. So loss of seagrass, huge increase in macroalgae. What's going on? So this is really the thrust of what I wanted to talk to you all about today, which is kind of coming up with a hypothesis, and that's what it is right now. It's really more of a working hypothesis on what might have occurred. And so obviously when we go back to 2017, we know Hurricane Irma passed through the area in September of 2017. In fact, the eye of the storm was about 30 kilometers away from the east wall at its closest point. And so hurricanes certainly have been documented to have an impact on seagrass, an impact on macroalgae, and especially that is the case when you have what we would consider pre-existing conditions. So I'm kind of borrowing that term from the medical field, but the bottom left graphic kind of illustrates that, where hurricanes have been happening for millennia. And so hurricanes in and of themselves should not be a causative factor to why we see a huge loss in grass and a huge increase in macroalgae. But if you have pre-existing conditions, going back to this idea that you have elevated nutrients in this estuary, you have the potential for eutrophication. So these seagrass are already stressed. And then you throw a hurricane on top of that, that could tip that balance towards a wholesale loss of grass and an increase in macroalgae. So that was one of the ideas that we had kind of kicked around as to maybe explain why we saw that huge loss between 18 and 20. But the other one, of course, that everybody is probably very familiar with is that shortly after the passage of Hurricane Irma, it kicked off a red tide event that lasted through January 2019. Worst red tide on record for this region. We're all familiar with the fallout of what occurred during that time period. So red tide certainly can play a major impact in all sorts of ecosystem function. But one of the things that I thought was interesting is when you really start to drill down on the direct impact of red tide on Charlotte Harbor, the harbor itself was largely spared the brunt of the red tide event itself. That is not to say that it was not spared or that it was spared the overall effect of the red tide, but Karenia brevis and its occurrence was largely absent in much of the harbor itself. So what's going on? Well, one of the things that we look at is the hydrodynamics of the estuary, and there's been some work that has been published to suggest that given certain weather conditions and certain hydrodynamic conditions, you can get water that gets entrained from the south up along the east wall of Charlotte Harbor. So Charlotte Harbor kind of, if you think about it, the circulation in the harbor is sort of in a counterclockwise direction. And so some of that water at certain times, not always, but at certain times of the year, will move up through Pine Island Sound, through Bokeelia, and then end up along the east wall. So we think that that could have had a major impact on why we saw this proliferation of macroalgae and loss of seagrass. Why is that? Well, it wasn't the red tide per se that was driving that, but maybe what happened afterwards. So this is where we use the term the hangover effect, because it's not the red tide, it may be what happened after. And what happened after red tide? Lots of dead fish, lots of decomposing phytoplankton, and we think that that may have had a major role. When we look at that from more of a chemistry perspective, what we see is that that the decay of fish carcasses, for example, has the potential not only to release large quantities of nutrients that are bioavailable, but specifically ammonia. So if you think about what really can spark an algae bloom, it's not total nitrogen. So it's not the total amount of nitrogen, but it's the species of nitrogen that matters. So if it's bioavailable, even if it's bioavailable, is it nitrate? Is it ammonia? And ammonia is much more effective in terms of fueling this algal growth than nitrate, even though nitrate's bad too. But in the case of decaying fish, we think that ammonia release may have really triggered a large part of what we saw along the east wall. The graph that you see on the bottom of the slide is ammonia data from water quality stations collected along the east wall, and you can see that there's a distinct spike in the ammonia concentration in 2019, which could have, again, been at least, from an observational standpoint, a result of this decay of the aftermath of the red tide, what we're calling this, this hangover effect. And interestingly, there's some literature that was published on Caulerpa prolifera, which is kind of the more common or the more well-known species of Caulerpa, that about 81% of the total nitrogen that it acquires is in the form of ammonia. So there's at least some anecdotal evidence to suggest that this aftermath could have driven or kicked off a lot of the algae blooms that we saw along the east wall. So one of the things that we did after kind of coming up with this working hypothesis is we wanted to look at the potential for how much nitrogen decaying fish could provide. So we used this 2,000 tons as a hypothetical amount of dead fish. And where did we come up with 2,000 tons? Well, we came up with that number based on, at that time, what we found in the literature, what we found in the media as far as the amount of fish that were being scooped up along the beach. So this is just a number that we're using as a hypothetical number, but it's roughly about what we think in terms of how much dead fish were scooped up in the beaches. It doesn't include the number of dead fish that were free floating in the water. But using that number of 2,000 tons, what we can do is we can convert that to a total nitrogen load. Am I still? Yeah, there we are. So the total nitrogen load, when you look at 2,000 tons of fish, converts to about 12,000 kilograms dry weight of total nitrogen. To give you a kind of an idea of how much load that is, that represents about 10% of the total annual load of total nitrogen coming from the Peace and Mayaca rivers, from the gauged portions of those rivers. So imagine 10% of a whole year's worth of load coming from 2,000 tons of dead fish that are being released, and potentially being released largely in the form of ammonia, which is really a desirable form of nitrogen for algal growth. Now, that's not the only part of the story, because the other part of the story is you're not only potentially getting nutrients coming from these dead fish, but also from the dead and decaying seagrass themselves. So we lost a lot of seagrass between 2018 and 2020, about 1,760 acres along the east wall. So if we take that 1,760 acres, and based on some of the work that was done by Tomasco and others, we are able to take that and convert that to an estimated total nitrogen load. Now, depending on the method that you use, you come up with a range of anywhere between 6,200 and over 13,000 kilograms dry weight of nutrients that would potentially be bioavailable to these algal, to these filamentous algae that we saw proliferating along the east wall. So not only do you have the potential for nitrogen release from dead fish, but you also have the potential of nitrogen release from the decaying and the dead seagrass themselves. So you kind of have this 1-2 punch, so to speak. So this is what we're kind of calling the hangover effect. And again, this is a working hypothesis, and it's based on the observation of this unprecedented seagrass loss along the east wall accompanied with this proliferation of macroalgae. And again, Charlotte Harbor was largely spared the direct impact of the red tide, so it's not the red tide itself, it's what happens afterwards that we think is what potentially could cause this to happen elsewhere. These large increases in ammonia-rich waters could cause these algae to proliferate. And so in the context of sublethal stress, in the context of these systems already being under stress by increases in nutrient loads, adding this pressure could be a causative factor for why we saw this loss in seagrass. And I want to pause here and talk a little bit about what happened after Ian, because we have an opportunity now to take this phenomenon and apply it to Ian. Now, there's a lot of differences between what happened in 2017, 18, and what is happening now in 2022 and 23. And so taking this working hypothesis and applying it to what we are now currently experiencing after Ian is going to be an interesting comparison to see if the same thing is happening after Ian that we saw after Hurricane Irma. One good thing is that we're not seeing this prolonged red tide event like we saw after the passage of Hurricane Irma, and knock on wood, that continues. Again, like everyone else in the session before, I want to thank all our partners. We can't do this alone, so definitely the Aquatic Reserve staff, FWC, the NEP, and all. This is obviously not an exhaustive list, but we always want to give a shout out to our partners for all the help that they provide. And with that, that's the end of my talk, and I guess I'll go ahead and pass it on to Miles. I think you're up next. Thank you.
All right, hi. Is this on? Yep. All right, hi everybody. I'm Miles Medina from University of Florida, the Center for Coastal Solutions. And I'll be presenting some empirical work I did as part of a much larger project, a one-year project that we undertook at CCS and just wrapped up about a month or two ago. This is work that we collaborated on with DEP, who provided funding, as well as the Economic Impact Analysis Program at UF IFAS and the Center for Public Interest Communications at UF. So just a brief overview of this project. There were, a lot of different science components here, from the empirical work I'm going to talk about, other work to understand estuarine hydrodynamics with some field work and some really cool observations from ADCPs, current profilers, and different things out there. We also had watershed modeling and SWOT, 3D modeling using ROMs for the coastal ocean to understand pollutant transport. And we had some computer science folks doing AI enhanced monitoring using remote sensing data for red tide, as well as in situ data, and then some economic work to understand how water quality and environmental things affect the economy and vice versa, and stakeholder engagement to understand information needs and biases among stakeholder groups and the public. So for my part, on water quality dynamics, the goal was to use approximately 20 years of water quality monitoring data from the Peace River Basin and the estuary to first of all understand changes in water quality over time. So there's a big trend analysis component here. We can use these results to identify some hotspots in the basin in different gauged locations. And then there's some preliminary work on causality around red tide that I'm going to share today as well. So brief overview of the results. First of all, nitrogen concentrations in the estuary are above the estuary's numerical criterion and trending upward. So some alarming news there. The map on the right is showing different nitrogen hotspots that I identified using trend analysis throughout the basin, from the headwaters near Lake Hancock all the way down to the estuary. And I'll build up to this map in the next few minutes. And then finally, this was quite surprising, just some preliminary analysis along the lines of what I published last year on red tide and Lake Okeechobee and the Caloosahatchee River. there does appear to be a link between nitrogen loads coming out of the Peace River and the dynamics of red tide blooms throughout Charlotte Harbor. And I'm going to use the word preliminary a lot just to emphasize that, but it's something that I'm continuing to develop. Okay, so onto the trend analysis. I want to start with the water quality data themselves. So if you've worked with water quality data in the past, you know that there's a lot of front-end work that goes on to clean up the data, get it into shape, to be able to draw some reliable inferences from. And for this DEP project, we just only used data from WIN and STORET. I am expanding the data set for what I'll ultimately publish to include data from SwiftMud and from CHNEP that are not yet in the WIN database. But anyway, we went through some very meticulous cleaning with these data, documented it in these R Markdown documents shown in the bottom left, so that it's reproducible and transparent. And this handles kind of lingering issues that, in a lot of cases, WIN isn't even really designed to address. And then the next question is, where do we have data that we can actually use for this kind of analysis? So I built a dashboard with the screenshot on the bottom right. If you've ever gone into WIN and it's not clear where to start, like I don't know where, which stations actually have enough data to support the analysis I want, built this dashboard to kind of support that and identify over a dozen locations in the Peace Basin that can support this kind of trend analysis. Okay, so ultimately the trend analysis includes about a dozen different water quality parameters. So this is nutrients, oxygen, BOD, things like this. For today, I'm just going to focus on nitrogen and phosphorus. We're looking at trends in the estuary as delineated by the CCHMN stratified sampling program. So that's the polygon on the bottom of the picture. And then we have 14 locations within the basin that are pretty data rich, or approximately 20 years of data to form a trend analysis. I also want to give credit for the method itself to Marcus Beck and his co-authors who published a really cool, sophisticated way of doing trend analysis early last year. So just a rough kind of intuitive overview. We start off with water quality observations. We fit a GAM, or a generalized additive model, that can capture the trend in the data over the long term, whether that's linear or nonlinear, can capture seasonality. So you can really capture some complex dynamics here in a way that is pretty different from the typical Mann-Kendall analysis. From there, from the GAM fit, we can estimate a metric. Here I'm using the annual mean concentration. There's uncertainty attached to each mean estimate. So if you've got fewer data points in a given year, or you had a particularly volatile year, you're going to have a wider confidence interval. And from there, then finally we get to estimating the trend over a given period of time. So for a given 5 or 10 year period, for example, we can get a familiar up or down determination about the trend in the selected metric, the annual mean concentration in this case. Okay, so in terms of results, this is total nitrogen in the Peace River estuary from the early 2000s up into 2021. On the top right, you see the GAM fit in blue over the data, which are the gray points, on a monthly basis. These are CCHMN data. Then on the bottom two panels, you see the annual mean concentrations for total nitrogen. And that's the same between the two bottom panels. The only difference is that we have a 10-year trend in the middle panel and a 5-year trend for 2017 through 2021 on the bottom panel. And in both cases, the 10-year and the 5-year trends are significant upward trends, and they are, you see that it's exceeding the estuary criterion of 1.08 milligrams per liter. So this is kind of the worst case category where concentrations are high and they're getting higher. So that's nitrogen. Total phosphorus, somewhat different story. We've got the GAM fit on the top once again. And then with the annual means in the bottom plots, we see that the concentrations on average are consistently below the threshold, the criterion of 0.5 milligrams per liter. Over the 10-year period, 2012 through 2021, it's been sort of flat, no significant trend. And perhaps a bit of good news, over the more recent 5-year period, we see a significant downward trend. Now you have to keep in mind this is these are observations from the water column, the first meter of depth. So we're not accounting for bottom sediments or biota here, just the water column. Now, one of the contributions from this work is developing a workflow that allows us to dump in data from an arbitrary number of monitoring locations for any number of water quality parameters, and then pump out results, do all the number crunching. And so here I'm just presenting a subset of those results, and ultimately I will publish results from across all the CCHMN strata, all different parts of Charlotte Harbor. But the table on the right is basically summarizing these trend results and interpreting them with respect to the estuary-specific numeric criteria. We can put in a threshold and then determine whether the most recent mean in the record of analysis is above, below, or near that threshold. So for example, in the first cell in the upper left, we see a red up arrow. So this indicates that there's a significant increasing trend in total nitrogen, like we saw on the previous slide. And the fact that it's red reflects the fact that the 2021 mean was well above the threshold, that criterion of 1.08 milligrams per liter. In contrast, if you scoot to the right in that first row, you see a down blue arrow. So that was that 5-year downtrend that we saw for total phosphorus. And the mean was for 2021 was below the threshold. Now, if you look down the columns for nitrogen, total nitrogen in particular, you see a lot of red. So a red up arrow, some red dots. The red dots indicate that over the 5-year period, we've got no trend, but we're above the threshold. So this is nitrogen concentrations that are consistently above the selected threshold, the criterion. And so if we consider red up arrows and red dots as hotspots, these are situations where things are above the threshold and either stable above the threshold or increasing further away from the threshold. We consider those hotspots. We can throw those up on a map, and this is what we see. So for nitrogen on the left, all those dots indicate nitrogen hotspots, where we're either consistently above the threshold over the 5-year period or above the threshold and have an increasing trend. So we see that the hotspots span from around Lake Hancock in the headwaters all the way down to the estuary. Most of the locations that we looked at were nitrogen hotspots. And then on the right, you see phosphorus hotspots. They're fewer in number, but interestingly, 3 of the main stem stations are hotspots for both nitrogen and phosphorus. So that's Peace River at Fort Meade, at Zolfo Springs, and at Arcadia. Now, if we overlay these hotspots with land use, we can see, first of all, the Peace River Basin, of course, has a lot of agriculture. That's the yellow. And then we can see that there's quite a few hotspots for nitrogen and or phosphorus nestled in the agricultural areas. And likewise, for mining areas that are that pink blob to the north. Now, you don't see any hotspots in the coastal, urban, or residential areas in gray, and that's simply because we don't have enough data for that area to do this kind of analysis. I would suspect that stormwater runoff and septic tanks would probably lead to some hotspots in the urban area as well. Okay, so now I'm going to shift gears and talk about the preliminary causal work that I did. So this is very much in line with what I published last year on red tide and nitrogen loads coming out of Lake Okeechobee and the Caloosahatchee River at S79. This was surprising to me because, of course, we know that Peace River nitrogen loads are much lower than loads coming out of the Caloosahatchee. So I didn't necessarily expect to be able to detect a causal influence. But in fact, the first analysis I ran looking at total nitrogen concentrations at the Arcadia station did provide a positive result in terms of causality with red tide. And this is based on the same red tide data I used for the Caloosahatchee study. So what's interesting here is that this Arcadia station is nestled in an agricultural area. It's pretty far inland, well north or upstream of any tidal influence in the estuary. And so what this indicates, suggest for now is that what happens in the Peace River in terms of nutrient loading doesn't stay in the Peace River. It potentially has broad effects for water quality throughout Charlotte Harbor. And furthermore, and I think this is relevant for the hangover effect that Chris was just talking about, we do see delayed effects as well. So the effect of this nitrogen loading can occur in the same month in terms of red tide, or up to 6 months later, and the peak influence seems to be at around 2 or 3 months. So I've got to continue working on this, vet these results a bit more, and further investigate, but it is a very interesting discovery, somewhat surprising, to be honest. I mean, it's not surprising that the loads would contribute to red tides, but that it would be detectable in the data like this does seem pretty important. Okay, so to wrap up, in terms of the Peace River, we saw hotspots all over the place, especially for nitrogen, so it suggests that basin-wide interventions are necessary to improve water quality in the estuary and perhaps in Charlotte Harbor more broadly. So this can be everything from septic to sewer conversion, infrastructure upgrades, treatment wetlands, and so on. I am working on publishing a paper to present a 20-year history of water quality for Charlotte Harbor based on the trend analysis and the nice consistent record that we have from the CTHM program. And then further empirical investigations and watershed and estuary modeling like we did for this Peace River Basin project can shed light on nutrient hotspots, pollutant transport, and support development of an RA plan for this area. And the empirical tools that we developed are relocatable. We can use the data dashboards, the trend analysis workflows, the causality analysis in different parts of Florida as well. And I just want to end with some broader context, and this is based on conversations I've had recently with Dave Tomasco at Sarasota Bay Estuary Program, who provided the graphic on the right. Like I was saying, the loads for nitrogen out of the Peace River are much smaller than the Caloosahatchee. And so it's an interesting problem. I mean, on the one hand, I've got preliminary results showing a link between the dynamics of nitrogen coming out of the Peace and red tide in the harbor. But on the other hand, Caloosahatchee River nitrogen just completely dwarfs loading out of the Peace. So the argument that Dave has been making lately is that, if we want to get this right, we have to get things right with Lake Okeechobee discharges, Caloosahatchee River discharges. Without that, there's only so much we can do addressing loads coming out of the other rivers. Fortunately, I have been engaged with the Army Corps. I've presented to them, and they are interested in seeking some operational guidance to incorporate red tide as a decision criterion for lake discharge decisions. So this is an area I'm interested in pursuing further with research, looking for funding for that. So if anybody has ideas for getting funding or collaboration on this more operational guidance for the Army Corps, definitely please approach me. And there's my email address if you don't run into me today or tomorrow. And that's all I've got. Thank you very much.
Good morning. Our previous two talks mentioned modeling, but I'll actually step into modeling. Hopefully, I'm not going to make it too boring. As a model of many years experience, Caloosahatchee estuary has been one of my focus, and I have worked on a spectrum of models, especially water quality models, that are from very simple ones like box model, which we call zero dimension, and to the real very complex ones such as full coupled hydrodynamic water quality and three-dimensional. I would like to share a secret. I would like to volunteer a secret that many in the model may not agree with me or may not willing to say that. That's, as a background, that's, I would say the major uncertainty, actually challenging in water quality modeling actually that's the kinetic rates. The kinetic rates, that's a really the results of very complex biogeochemistry processes. So, but they're so hard to quantify. So why do I say that? If we look at the governing equation, it's a very general equation I listed there in this slide. That's a very general equation for water quality constituent. So the first term is really just a rate of change, and also transport advection. Then on the right we have diffusion, but the major term, as long as water quality is concerned, that's the kinetic rates. We call the first order kinetic assumption, but the rates are really the issue here. Just for example, when we modeling phytoplankton, this is a net growth rate, that's mu, and that's a sum of a primary production rate, which is G, and respiration, and minus mortality. Mortality is very much related to predation. So we have some empirical relationship that we think we can model these rates, but really it's hard and it's not easy, and we have a lot of uncertainty in each of them. But in particular, that's the predation, that's the M, because we really have very little knowledge about this predation. Therefore, it's very hard to quantify them. So I already listed that equation because if we are modeling just the advection diffusion, that's a conservative species like a salinity, the hydrodynamic model have a really good solution, or can really model them pretty well. So, but at that time, then we have a lot of trouble. But from modeling perspective, really not the model itself. The model itself, if we can quantify this mu term, the kinetic term accurately, then I really don't have doubts that the current mathematical model, numeric model can do that pretty well. So really it's the quantification of this kinetic term that's the trouble for us. Now, so with that said, we realize that kinetic rates are critical for assessment of water quality condition. We'll see that in our next slide as well. And so, but we think, through our exercise, modeling exercise, as this talk, really focused on that, monitoring data may provide an indirect way to estimate these rates. So that's really the focus of this talk. Now, this is the actual model. I don't really need to worry too much about the mathematics, but that's the tidally averaged, cross-sectional averaged, one-dimensional model in its general form. It's extremely simplified. So with a sort of like flat and rectangular S-tree with constant parameters or like rates, we are able to find an analytical solution. That's on the small up right corner. That's the analytical solution, even though it's very simplified, but it still, I think, can give us some really good clue. One important finding from this simple solution is that the upstream boundary condition have a controlling effect. What does that mean? That means, something comes down from S79 and maybe even can trace it back to the canals and the lake. That can have a controlling effect That's all. It's an important source of algal biomass. That's very important, especially if you have a algal bloom happening in the upstream, like in the lakes. Then the second conclusion, the simple analytical solution says that residence time is very critical. And if we have this net algae growth rate higher than the flushing rate, the flushing rate actually is the inverse of residence time, then potential algal bloom may develop. But this algal bloom I'm talking about really is what's originated in the estuary. This should be separated or distinct from what's going on from the upstream, like lakes, the impact downstream. So this is the algal bloom I'm talking about. It's the algal bloom that may originate from the, say, Caloosahatchee estuary itself. Then the third, conclusion or result from this simple solution is that higher net growth rate can lead to higher chlorophyll A maximum in the estuary. You can see from that left right corner of the curves. That's I think I should blow it up somewhat. So it's a longitudinal distribution of chlorophyll A or algae. And you can see, there are different curves there. The lower curve is a result from the lower net growth rate, nu. And the higher the growth rate, the higher the algae concentration in the estuary. So, but this actually gives us the clue. Even though it's a very simple solution, what that means that from the distribution and from the shape of the profile that the solution gives, that we can see that higher rates, you have a higher chlorophyll maximum, and this chlorophyll maximum actually is being observed in the estuary. And has a well observed, qualitatively discussed. But this longitudinal tells us that there's some clue from this solution that high rates, high chlorophyll maximum. So we can maybe we can utilize this kind of shape to try to back estimate what the rates are, because you have high rates, you have a high chlorophyll A maximum. So what we did, we cannot use that simple analytic solution, but we need to further develop so that the model can actually solve can be solved more realistically for real estuary. So that's what we did, further develop that analytical solution. We call it semi-analytical solution for that real estuary. So here's the methodology. I really don't have to worry too much about the details. It's a salt balance approach. What does that mean? That means we use salinity as a known quantity because salinity is really a result of adiabatic diffusion, transport. So it's a good indicator for transport. So that should equally applies to other constituents. So use salt as an indicator that can help us easily solve that 1D equation. And then we also have to construct a green function, which is a tool, so we can compute the nutrient and algae. And I actually also need to use an iterative approach. So what are the inputs for this model? It's discharge as S79. As I already said, we need a salinity. This time we the salinity from the CH3D hydrodiatic model that we routinely use. Now we also need boundary conditions. These are from surveys. So we are actually make application of this model to monthly surveys that the source for water management try to collect samples regularly monthly and bring to the lab for analysis for nutrients, chlorophyll A, DO, etc. So these survey data points at the upstream S79 and the downstream CES09 are used as boundary condition for this model. Then we actually use an empirical model to compute the growth rate, but essentially you still need to calibrate these empirical parameters involved in that empirical model. So essentially this rate is still calibrated, so that's important. So what are the results? The results are, I have the chlorophyll A, model with observed. We have R square value of 0.5. It's not great, but it's decent. That's actually, so I have to say, each data point there is for each survey, each monthly survey. Then we have, I put total nitrogen as an example there. Actually, we actually did perform on the other nutrients as well. So the R square between survey data and model is 0.8. That's actually pretty good. So, but the focus here is really the lower panel. What are the calibrate net growth rate? We have it's probably, I don't know if it's really very visible. So, this net growth rate, from 1999 to I think it's probably 2017. These are the rates estimated or calibrated results rates from this exercise. And you can see that we not only have positive rates, which really indicate a net positive growth. We also have negative rates, which really means that it's not growth net. It's a loss. That's possible. And actually, we are missing some good survey data in between, say, 2004 and 2006 or something like that. So we lost some survey data because this model requires a good number of points. If we're not sufficient point, then it's discarded. So, but anyway, that's the rates that estimated as a result from this model. Just very experimental, very preliminary. How good these rates are, really I don't know, honestly. But I would say that's a step that we can utilize probably and better to compare with later more actual field studies, what really net rates are. But what does this exercise tells us? So first one is net rates are very important to forecast algal bloom. Why? Because I already pointed out when the net growth rate is greater than flushing rate, then you probably have algal bloom setting in the estuary. So also higher net growth rate than higher algae concentration. And actually, you can stop this algal bloom if we know beforehand. You just need higher discharge to stop or prevent this algal bloom. But we need to know what this growth rate is. Then this experiment suggests that it is possible to infer this net growth rate from survey data. That's what we call synthesizing. Then the other important conclusion that it's the external sources that's from upstream that could have a really significant source for the algal biomass, and that is especially important when you have a upstream algal bloom event. That's all for me. Thank you very much.
my pleasure to be here. I'm Rebecca Cray. I have a lightning talk, so I'm just going to jump right in. So Estero Bay is the water body located between Fort Myers Beach, South Fort Myers, Estero, and Bonita Springs. It was established as a aquatic preserve in 1966. It's actually the state's first. And it was established at the urging of local Lee County citizens, primarily fishermen and conservationists, to protect the water body from development. So the goal of the work that the Estero Bay Aquatic Preserve staff do is to maintain the water body in its essentially natural condition for the enjoyment and benefit of current and future generations. One of the ways that we do this is by monitoring the habitats and the water quality within Estero Bay. The program I'm going to be talking about today is a near continuous water quality monitoring program. This program was established in 2004 with the first 3 monitoring stations, EBO 1, 2, and 3. These stations collect water quality information every 15 minutes and have been doing so pretty much uninterrupted since that time. The readings that are taken are temperature, specific conductivity, salinity, pH, dissolved oxygen, depth, and turbidity. And with this abundance of data, we are able to ideally achieve some of the program goals, which are to establish baseline water quality, evaluate the daily, seasonal, and long-term trends, and to quantify the effects of specific events. So some of these station histories are fairly straightforward. Others have gone through some changes lately. So again, the first 3 were established in 2004, and EBO 2 has been recording through present. EBO 1 recorded through the hurricane, but the dock that it was deployed on was severely damaged, so we were able to retrieve it and the data from the hurricane, but it has not been deployed there since. We are setting up a new station in that area. EBO 3 was never recovered post-hurricane, but will be reestablished once the piling is replaced. And EBO 4 was set up in 2021 to fill a perceived data gap. There's grab sampling in that area, but we wanted to complement it with some continuous data. So for the long-term trends today, I'm going to be talking about EBO 1, 2, and 3. And then for the specific events, I'll be primarily focused on EBO 2. So the long-term trends are shown on this table. The up arrows indicate an increasing trend over the 2005 to 2022 time period. The downward arrows indicate a decreasing trend, and the dashes indicate no statistically significant trend. These were done using seasonal Mann-Kendall tests on the monthly averages of the data at each of the stations, and then that all category is the average of EBO 1, 2, and 3. So as you can see in Estero Bay, the temperature has been increasing over time, salinity decreasing, dissolved oxygen increasing. For the most part, at 2 of the stations, and overall, pH has been declining to indicate a more acidic trend, and turbidity is kind of a mixed bag. One of the stations showed an increase, the other 2 a decline, and that averaged out to not being statistically significant. And these changes can have implications for the habitats and the organisms that call Estero Bay home. This graph just shows that, that monthly average salinity data and the declining trend line. This graph is, I'll orient you to it. So the black line shows the 2022 data from EBO 2. The colors are indicative of different percentile ranges of the historical data. So the blue would be the lowest 10th percentile, the red the highest 10th percentile, and the yellow is kind of that 25th to 75th percentile range, or what we would consider kind of average, based on the 2005 through 2021 data. And so you can see that plotted on that background, the 2022 data had several portions of the year, and these are daily averages, several portions of the year in which the daily average dipped below what had been recorded previously or was kind of hanging out in the lower salinity ranges. And I look at these every year to kind of get a sense of what's going on in the bay for that year. All right, so transitioning away from kind of the long-term trends to look at specific events. So to orient you to these graphs, they're all going to be fairly similar. The x-axis is the time period from August 1st through October 31st. The green is the 2022 data, and blue is 2017 data. The first vertical red line indicates Hurricane Irma on September 10th of 2017. The second one is Hurricane Ian on September 28th of 2022. So each of these two hurricanes affected Estero Bay water quality very differently. As you can see from the depth graph, Hurricane Irma in 2017 pushed the water out of the bay to drop it to about 1.5 meters or 4 to 5 feet below background depth levels, whereas Hurricane Ian forced water into the bay about 3 meters or 10 feet above background levels. Both of the hurricanes corresponded with dips in temperature, so that in that way they're similar. The salinity data for the two, I did use EBO1 for this as well because it showed an interesting difference. But in 2017, the salinities were already low due to high rain and flooding prior to Hurricane Irma, and then they dropped again when Hurricane Irma hit. With Hurricane Ian at EBO2, there was a dip in salinity, but less so than had been experienced with Irma. And at EBO1, you can actually see an increase in salinity, which makes sense because the Gulf waters are more saline, and as they rushed in, they made a salinity spike. You can see that there's a little bit of a signature of dissolved oxygen when the hurricanes hit. There's kind of a plateau effect, and you don't see for a few days the usual daily fluctuation of the dissolved oxygen right when a storm and right after a storm has hit. And then in this final graph, you can see the turbidity spikes or the water clarity spike or declines right in conjunction with the storms. They both had fairly large turbidity spikes in association with the storm impact. And you can actually see in the blue 2020 or 2017 data before Irma that flooding event and high rainfall event had also caused significant turbidity. And then you can see in the green after Hurricane Ian that there's a lot of high turbidity spikes after the storm that likely correspond with, all of the runoff and everything that kept occurring for a little while afterwards. And like I said, that was a lightning talk, so that's actually all I have. So thank you guys for your time, and I'm looking forward to any questions.
All right, so now we're going to go into question and answers. If you haven't already, please open your Menti and start entering questions. We do actually have quite a few already in there, so we're going to turn over to that now. And presenters, please feel free to jump in and start answering questions as you see them appear on the screen.
I can I can start with the top middle one about the red tide events. The analog on the East Coast. This is as I said, this is kind of a working hypothesis, and we haven't really looked at it on the East Coast. I'm assuming you're probably referring to the Indian River Lagoon and some of the issues that have occurred there. But I think this is something that can be applied to other estuaries. We've been looking at this actually in Tampa Bay, not specifically related to red tide, but more or less related to the persistent the algae blooms that you see in Old Tampa Bay and some of the non-red tide or non-Carenia bloom events, and applying that same idea to some of the seagrass losses that we've seen in other parts on the West Coast. But to my knowledge, we really haven't worked specifically on the East Coast, but I think that would be something that would be worth looking at, is applying that same idea on the East Coast as well. I think so. The question on the top left, relative to nutrient levels having an effect on blue-green algae blooms. We were really focusing mostly on the macroalgae, but we didn't really see, when you look at the water quality data before and after that red tide event, the chlorophyll data, which is really kind of a proxy for your phytoplankton in the water column. We weren't really looking at that so much as we were looking at the proliferation of the macroalgae and its effect on the seagrass loss. So we weren't really focusing too much on the blue-green side of things. Maybe Miles can add a little something to that, since he's focusing on some of the red tide impacts of nutrient loading into the estuaries. Yeah, so another question on the right side of the screen, relative to the increase in chlorpa on the east wall after the Irma red tide. We didn't really see a whole lot of prolifera on the east wall. I don't really think there is much. There's certainly chlorpa prolifera out there in the harbor, but it's not as much of a dominant feature as some of the other estuaries where we see, like in Tampa Bay, for example, where there is a lot of chlorpa, especially in Old Tampa Bay, of the chlorpa prolifera specifically. And I focused a lot on the chlorpa fastigiata in my talk, but that's not to say there aren't other macroalgae. There's certainly a lot of red algae. There are tons of different types of green algae as well. What we thought was anomalous, though, after that red tide event, starting really in 2018, was the proliferation of this particular type of chlorpa, not prolifera, but fastigiata, which is a rather odd chlorpa in my experience, having a lot of the characteristics of almost like a lyngbia or a chaetomorpha, where it's very filamentous in nature, but it can also attach as well. So it's kind of an interesting species of chlorpa that I was not familiar with. So it caught our attention because there was so much of it along the east wall. And a lot of that also is entrained in those tidal tributaries, those mangrove channels that you get along the east wall, as well as on the west wall as well. It's not specifically only to the east wall, but that's where we saw the greatest loss of seagrass concurrent with that increase in macroalgal abundance. So that was the area that we were focusing on for this particular work. Anyone else?
I'll take the bottom right there. I think maybe the end is cut off a little bit. Oh, here we go. Okay. So the question is about, I think, nutrient co-limitation. Do you think there's an interaction of total nutrients, both TP and TN, that factor into results even if TP are within criteria? Yeah, so I mean, that's a great question. This kind of analysis is really about finding sort of the limiting factor. I think that there's a good argument that could be made that there's probably co-limitation in certain places at certain times. But looking at things on an aggregate scale and on a biweekly or monthly sort of time frame, it does appear that nitrogen is acting as the limiting factor here. So, in physical terms, does TP matter? Yes. But in terms of intervention, if TN is having kind of a controlling effect on the dynamics of the bloom in terms of the intensity or the duration, then whether you increase TP or decrease TP maybe isn't really going to matter because there's enough of it anyway. It's abundant relative to the relatively limiting amount of TN. So in terms of intervention, I think TN is more important on this scale, but I think it is an important thing to keep in mind that co-limitation is a thing and it matters. Yeah.
I wanted to address the bottom left, and Miles, maybe get you into the discussion on this too, because it brings up an interesting point, which is this, this idea of legacy nutrients, and specifically what we've been thinking a lot about is recycling of these legacy nutrients. And I'm intrigued by your figure that you had looking at the increasing trend in nitrogen in the tidal Peace River, and I'm wondering if there's any if there's any interaction between increasing sea level rise and that legacy nutrient. So the work that I had touched on, the stuff that Gene Turner had done back in 2006, was really looking at sediment cores in that tidal Peace and Myakka area, and definitely what we were finding is that there's deposition of those organic sediments that, and to your point too, I think you made the point that we're only looking at the top portion of the water column. So there's a lot of action that's happening in the lower portion of the water column, and arguably one could say that most of the action is really along that sediment water interface. So I'm just wondering, what your thoughts are on addressing that idea of legacy nutrients, and also in the context of these pulsed events. So you get these massive loads of nutrients like what presumably happened after Hurricane Ian, and how does that affect what we're seeing at the surface of the water column? I'm just wondering what your thoughts are on that.
Yeah, I think it's an important point. I don't know if I have anything very insightful to say on the spot, but I think it's worth looking at. I mean, this should be part of the story. I think publishing this kind of water quality history paper is engaging with that. And another kind of caveat to the analysis I did was that looking at trends in the estuary really completely ignores tidal cycles and when the samples were taken with respect to the tidal cycle. So you could see artificial things happening if you don't account for that, and we typically don't. But yeah, I think with climate change and sea level rise kind of mobilizing nutrients, that's a really important point. Yeah, I do want to give that some more thought. Okay, this is an easy one to knock out. Where did the 1.08 threshold come from? That's the estuary-specific criterion for total nitrogen in the Peace River estuary. That's from Florida Administrative Code. I use that across the board as a threshold for even the basin stations, even though there are different criteria associated with different WBIDs and different things. You could drop in any threshold you want, but for simplicity's sake, I just went with the estuary-specific criterion, at least for now. Let's see. Okay, there's a few for me here. Do you want to take one?
Well, I was just I was just going to answer that middle question about how the total nitrogen load was calculated. So I didn't really go into detail on how we came up with those numbers, but they're basically, it's based on just spreadsheet estimates. So total nitrogen for dead fish is based on, you have let's say use the 2,000 tons. That's an estimated wet weight of total number of dead fish that you collect. So you just take 25% of that as the estimate of the dry weight, and then from that you calculate 2.8% of that dry weight is in nitrogen. So it's basically a very back of the envelope type calculation. With respect to seagrass, it's based on some literature values and some conversion rates of again, wet weight, dry weight of seagrass biomass, and then you just convert that to a total nitrogen calculation. So it wasn't measured, it was based on literature values and literature conversion rates.
Okay, so on the right there, since Ian hit in September 22, has there been any recent tests which would measure its impact on Charlotte Harbor's water quality? So I haven't yet looked at all that, and I know Brandon Moody is going to be presenting tomorrow on what some of the data say about Ian impacts. I've been focusing kind of deliberately on pre-Ian to establish a sort of story there before, to provide a context for that kind of analysis post-Ian. We did stand up a dashboard with data as the recovery effort was going on in the couple of months following the storm. And I think those data are going to be the basis of at least part of what Brandon presents tomorrow. What specifically defines a hotspot? So for this analysis, it's if the 2021 mean was at least 10% above the adopted threshold, which was taken from the estuary specific criteria, and the trend is either flat, meaning that you're consistently above the threshold, or the trend is up, meaning that you're above the threshold and further increasing. So that's how I defined hotspot for what I presented. To what contribute to the decrease in TP in the Peace River estuary? Why is the TN increasing? Yeah, I don't know. That's a good question. I mean, right now I'm at the stage where I'm just starting to kind of get the results. Making sense of them is going to be another issue, and I'm going to consult with Chris and others that have more local knowledge, Jennifer and Nicole as well, to get to that. Maybe you have some insight there.
Oh, I would say that in terms of the total phosphorus, we identified years ago one of the big hot spots to the Peace River was Lake Hancock, and in 2015, we did a project to basically hold the water back in Lake Hancock. That was really related more towards meeting our minimum flow for the Peace River. So it wasn't a water quality project, but what we noticed is that the concentration of total phosphorus simply by raising the lake level went down, as did the total nitrogen concentration in the lake. And so it could be that some of that reduction in total phosphorus may be simply because we're holding more of the water back in Lake Hancock. It's hard to tell, really, if that's an issue. I do have as well that question about why we see TN increasing at the same time. And I mean, I could talk about that all afternoon, but I'm curious to really drill more down into where we're seeing those increasing trends. It looked like, Miles, from one of the figures that you showed, the greatest trend is in that tidal portion of the Peace River, whereas in the upper portion of the Peace River, we're exceeding the threshold, but it didn't look like there were it didn't look like the trends were increasing in those other stations. So there's something going on in the tidal piece, and that's got me thinking, but unfortunately, I don't have an easy answer at this point to explain why we're seeing that, but that's definitely, I think, a very important finding from your work.
Yeah, that's kind of piecing together the story, I think, is the work that lies ahead. On the left, there's two questions about coastal part of Charlotte County. So this is the urban kind of residential area. Charlotte County recently kicked off their stormwater sampling program. How many years of data do we need to do this kind of analysis? So, I mean, I think 5 years is generally considered a good kind of trend analysis period at a minimum. So I would say that would be good. And then, would you be interested in looking at this data against other potential loading hotspots along the coast? Yeah, exactly. So this is something I've been talking about with Dave Tomasco in particular, and some others as well. I think looking at relative magnitudes of loads is very important. The argument Dave's making right now is that, if we don't get Caloosahatchee right, then sort of nothing else matters. It's kind of a necessary, but maybe not sufficient part of the solution. Are there plans to update the study with urban area? Yeah, as soon as they're available, for sure. We want to understand, septic and stormwater infrastructure, how that's influencing things, and given the proximity, of course, to the estuary and the harbor, that's important. There's a question about proving causality. So I could talk about this all night, but basically, if you think about correlation, let's say you've got two things, nitrogen and red tide, and you make a scatter plot in Excel, you may or may not see a relationship there because how red tide manifests depends on so many different factors, and the way that nitrogen can affect red tide depends on those other interactions as well. So the way this causality analysis works is it kind of implicitly, it's not a statistical approach, although it's empirical, it kind of implicitly takes into account all this complexity, the information that's shared between different variables in their time series dynamics. So when different variables interact, they kind of exchange information. There's a sort of dance, and you can draw an inference and kind of look for a signature of one variable affecting the other in the data. It's quite a bit more technical you could get with that, but that's sort of the intuition. There's a question at the top there about east and west coast with red tide. So, red tide typically doesn't loop around and hit the east coast, but there are blue-green algae problems in St. Lucie River and so on. So I think it's better established there that discharges from the lake affect, sometimes just transport algae cells. But then there can also be kind of nutrient loading effects as well. So I'm not sure that analysis is really needed there, but it is something that I've thought about before.
That middle question, I think, is a good one, too, about nitrogen loads of the Caloosahatchee relative to the piece, and does proximity play a role? I think the short answer to that question is yes, it does, and that sort of underscores one of the data gaps that we've been working with Brandon on trying to fill, which is looking at nutrient loading, nitrogen specifically, in these what we call the ungauged portions of the watershed. So those areas that are proximal to the harbor, where you get a lot of septic tanks, a lot of direct runoff via canals, those are really hard to quantify and measure accurately. A large part of it is due to the fact that there are so many canals, and also because it's tidal, and calculating accurately a load from a tidal reach is challenging. But I do think that proximity does play a role in that. So it may be that Caloosahatchee does have higher loads, but when you think about how the harbor circulates in general, most of the flow that's coming out of the tidal piece and the Myakka really hugs that west wall. And so there may be an opportunity to look at west wall dynamics versus east wall to sort of infer what is the impact to these more proximal sources relative to sources that may be more distal, coming from Pine Island Sound and Point South.
There's a question, can we scroll up just a little bit on the upper right? Or down, go into the past. Oh, yeah, okay. So let's see, mentioning the peak releases of nitrogen happen 2 to 3 months from Arcadia. What time of year was that prevalent? And then chlorophyll A. Okay. So that delay of 2 or 3 months, that's from the initial causal results. Again, I have to vet those a bit further, but what that indicates, I don't know yet. I haven't done the analysis yet on what kind of year, what time of year that's most prevalent. I would imagine it's the wet season, but I have to do some more analysis to figure that out. That peak at 2 or 3 months means that the peak influence of total nitrogen from Arcadia occurs with a delay of 2 or 3 months. And when I say influence, I mean on red tide blooms throughout the harbor. The question about chlorophyll A. So chlorophyll A is often used as a sort of proxy for algae in general, but those aren't the data I used for this analysis. That was K. brevis cell counts from NOAA's HABSOS database, which ultimately largely comes from FWC. And then there's a question about communication and with the public and with managers. So for the Peace River project, we actually had a dedicated objective about public engagement and understanding things, both from social media and from interviews with different stakeholder groups, where we spent an hour talking to people and coding up the results. I don't know if I have anything particular to say. I'm not as familiar with those results, but if you shoot me an email, I'd be happy to share the report that CPIC put together on that basis. I think there's some cool insights in there. And fortunately, with the work I've been doing the last few years, there has been good public reception from DEP, from the Army Corps, local governments, in terms of using the information and to make decisions on water quality.
I finally see some questions. Thank you. Well, I think 2 of them for me directly. The first one, you mentioned that you use light as a parameter in the model. So how do you measure it? Yes, we do measure it. We have in our weather station radiation. To measure radiation, we have the unit is in Einstein. So I think we have daily value, probably even higher than that. At least I use daily value in the model. So that is actually measured, it's not modeled. So, but used in the model because, apparently algal growth needs light. That's why it has to be there. That's the first question. Then the second one is monitoring effort in the Cruz-Hatchie sufficient to inform the models? That's a really a good question. It's not really easy to answer. Is it sufficient yet? No. But what is missing? That's the important part. So I really think what we're doing now, we have one that I would like to see is, just from modeling perspective, one is that right now we only have mostly grab samples, or that's kind of like happens monthly. That's not sufficient. But fortunately, we're having more continuous data. So that I would really like to see continuous data. The continuous data, like it's not necessarily like hourly. That's probably too. It's not probably not that much. But I'll take back my words. If we know there's blue events coming, we really want to see some very good frequency measurement, observation from like hourly, even hourly. That would be really good. I think we're definitely missing that kind. I know there's like in the St. Lucia we have global, and the SCCF has some continuous monitoring. That's really good. But the question, for us, really, how good are the gauges? How reliable they are. That's a key question that we. So right now, I'm really relying on these the district regular monitoring, because they bring to lab to do analysis. They're usually very reliable. Another very good survey event that's really going on, it's from district, is that the service data. That's a more one day event that they take the boat, it's a flow through, and you travel from upstream like S79 all the way downstream. That kind of data is really helpful. That's a kind of, I would quantify that as sort of like episodic event. Then you give us a longitudinal profile. That's what exactly my talk about. We could utilize those to have some sort of a sense how high the growth rate, especially the vital growth rate. There are other rates that if we measure nutrients that could be estimated. So that's yeah. Thank you. That's I guess maybe there's another one. I'll pause here to allow others.
Okay. I'll take a crack at a couple too. So any interest or funding for adding additional parameters like nutrients to the data science? So I would say interest is there. Funding would be needed, and there may also be there may be necessary like technological advancement before that's possible as well. I'm not as informed as I potentially could be about what kind of sensors actually exist for nutrient readings on continuous data loggers that would be compatible with what we use, but I'm not sure that it would provide as reliable of values as yet as grab sampling, which does occur in Estero Bay. Lee County Environmental Lab takes monthly sampling or monthly samples at multiple locations throughout the bay. Volunteers for the Charlotte Harbor Estuary Volunteer Water Quality Monitoring Network take nutrient samples, and we occasionally take some as well. So there is nutrient sampling, it's just not continuous as yet. So it is something we'd be interested in, but it's not something we're moving towards quickly, I guess, or that we are aware is an option right now. And then I'll go to the other one that I see for me. It looks like DO recovered quickly after Ian. Any thoughts on accounting for this? So I don't know that I can know for sure. And unfortunately, the station that we have data, the best data for post-Ian is EBO2, which is located fairly close to New Pass and to Spring Creek. And the freshwater inflow from Spring Creek is much less than some of our other freshwater tributaries. It's a much more Gulf-influenced station. So that's one of my thoughts as to why the DO is bounced back so quick, is because a lot of the Gulf water was what would be primarily would be sampled at that location. One of the stations that was in place for Irma, but not for, but that got knocked down by Ian, UBO3, located in the southern portion of Estero Bay near the Imperial River. I didn't show graphs of it because we didn't have Ian data for it. But after Irma, the DO was very low, hypoxic for at least a month after Irma. So I was actually very disappointed that that station didn't survive the hurricane, because I would have loved to compare those data and see what that part of the bay looked like after Ian with regards to DO. But I simply don't have that information. But yeah, that's the best estimate or accounting I can give as to why it looks like it came back so quick, is that the station that I was showing is primarily influenced by the Gulf.
Yeah, if I can build on that too. We didn't really talk about Lemon Bay because it's a little or lower Sarasota Bay because it's outside of our area here. But we saw the same thing in terms of DO. You know, we saw a big dip in DO, but within a couple of weeks, places like Little Sarasota Bay, Blackburn Bay, Roberts Bay, they recovered pretty quickly. And yeah, we think it's largely due to the connectivity with the Gulf. Just another thing too about, like, just to go back to nutrients on data science, I have a lot of experience working with some of these in situ probes. I've worked with DEP on deploying these nitrate sensors. They're made by Suna, and they're basically an optical nitrate probe. They work pretty well. They work really well, but the problem is that you're only measuring nitrate. So you're not getting the total nitrogen picture, you're only looking at nitrate. So they're somewhat limited in their capacity to really make ecological conclusions or decisions on. And then with phosphorus, unfortunately the technology isn't there yet to where we can use optical probes. There are in situ total phosphorus devices. We've used some of them, again, working with DEP. There's one called a Cycle P, which is literally a spectrophotometer in a can. It uses the same wet chemistry technique that you would use in a water chemistry lab, but they smush it into a cylinder and it's become submersible. So as you can imagine, if you're doing wet chemistry underwater in a can, exposed to the environment, it can be very problematic. So in general, we try to steer clear of using those types of technology. So yeah, I think to your point, the technology's not there yet, but hopefully that will be coming soon. I did see a question on the right concerning the 2022 seagrass maps that we published recently. And so the thing too that I always remind people whenever we talk about the Water Management District seagrass maps is that we base our maps on aerial photography, and that aerial photography is flown between December of the previous year and February of that year. So when we talk about 2022 seagrass maps, we're really talking about December 21 to February 22. So the long and short of that is it's all pre-Hurricane Ian. So the short answer to that question is that overall, the harbor has, it seems to have bottomed out. Some areas in the harbor saw an expansion in seagrass, especially along the west wall, but we also saw further loss. In the east wall, unfortunately, we did see continued loss in 2022 relative to 2020, but nothing near what we saw between 18 and 20. So hopefully, cross our fingers, no lasting impacts from Ian. have been out in the field with aquatic preserve staff, with Dave Blewett and FWC folks along the west wall. We've had staff go out with them on the east wall. And while, you know, things don't look great, they don't look like they've gotten much worse as a result of Ian. But again, it's still too soon to tell. So we're still watching that very carefully.
I think there's a question of dilution. It's not here, but I think I can answer. What models, most models can do that, actually. Hydrodynamic model and, well, basically the advection diffusion model, you know, coupled with, you know, hydrodynamic model that can naturally do the dilution. But in my model that I just presented, I actually use salinity as an indicator. So because salinity is the inverse indicator of dilution. So high salinity means that, you know, you have high seawater, that you have also relatively high dilution from the to the riverine sources. That's also doable.
I think a little further down there were a couple of additional questions for me. Let's see. Yeah, okay, to inform mitigation strategies, we were able to identify areas that share characteristics with hotspots, but that had lower P and N values than expected. So I'm not there yet, but that's a great question. That's exactly the point here, is to kind of target, you know, this is non-point source pollution for the most part. So to target within the basin which particular creeks or subbasins are contributing and amenable to some kind of intervention. At some point, you have to step away from empirical work and get into modeling, and that was part of our project. So Dr. David Kaplan at UF and his team developed, I believe, the first swamp model for the Peace River Basin, and that can help us distinguish different characteristics like the soil characteristics, hydrology, and so on. And then beneath that, are there any water quality trends on the Peace River that directly threaten drinking water safety? That's another great question. So the hydrodynamics team, I'd be happy to connect whoever asked this question with those guys if you email me. They did find that the kind of salinity wedge does intrude much further inland than expected, and to the point that the drinking water intake for the Peace River, Minnesota Water Authority is affected and needs to desalinate often. But fortunately, that is maybe more predictable than expected, because it's over the long term largely affected by astronomical cycles that are completely predictable. So there's some really interesting results there that, yeah, I'd be happy to connect you with the people that can give you more details.
All right. Well, we had a lot of questions. Unfortunately, we're out of time, so we do encourage you to reach out to the presenters using the contact information in the BIOS document, which is available online at the chdp.org website.